lighter. So this is the compressed one of the two experiments. Annual data volume, as you will still see me talking in this talk, I will make a lot of reference to the Highland Mercer LHC. That's an upgrade program to the accelerator and the detectors that will go live somewhere 2027, 2028. We'll see when it really goes live. And there is the Highland Mercer LHC sees an increase in the intensity of the beams, get brighter by times 6. The data taking rate goes up by times 6. In other words, we're not writing out 1,000 megabytes, but 6,000 megabytes. And the simulations go up by factor 3. And if you then multiply the numbers, you find that the primary data volume goes up per year by factor 30, reaching about 600 petabyte per year. Now, this is the current planning. It does not include the fact that we are expecting a reprocessing. So this is a single processed version of all the data on all the simulations. So the actual data, including reprocessing, may very well be more like an exabyte. And what exactly will happen, we'll see, because these numbers are still somewhat soft and may change due to planning. This talk is about R&D strategies and concepts in general to keep the cost roughly the same despite a factor 30 increase in data volume per year. And I will motivate the R&D via a detour on how the science is done. So let me start my detour. In a somewhat oversimplified view of the science is that what we do fits into one equation. There is something that we measure, which is a corrected yield. And that corrected yield is the cross-section, which is the physical process, the science that we're interested in, times a measure of the brightness of the beams. And so in the end, corrected yield is obtained by the observed number of beam crossings that pass some selection, divided by the selection efficiency. And the selections are developed and the efficiency is determined from simulations. So in essence, it's an enterprise that fits on one slide to give people a sense of what it's really about. Now, in terms of, if you want to dig a little bit deeper, it may be thought of as a big bang in the laboratory, meaning we gain insight by colliding protons at the highest energies possible to measure what gets produced at what rates, masses and lifetimes of the particles that get produced, decay rates, partial decay rates, and so forth. And from this information, differential rates and kinematic distributions, et cetera, But from this fundamentally reasonably simple set of measurements, we then derive the spectroscopy as well as the dynamics of elementary particles. Progress is made by going to higher energies and brighter beams, effectively, meaning more proton-proton collisions per beam crossing. And more collisions means we gain increased sensitivity to rare events. And more energy means we probe higher masses, smaller distances, earlier times. In physics, those three things are directly linked. You can think of them as a Fourier transform of sort. Being able to reach higher energies means we're reaching smaller distances, which means we're reaching earlier times in the universe's evolution. Now, one more word on what does spectroscopy mean and what does dynamics mean. Spectroscopy means what are the particles that exist and what are their properties. Dynamics means what are the forces between these particles. How do the particles couple to these forces? How do these depend on energy, angular momentum, et cetera? So the dynamics is the understanding of forces, the spectroscopy is the understanding of particle content, and together we develop a theory of how the universe works, in essence, at the smallest scales and the earliest times. Now, this is all I'm going to say about what the science is that we're doing. I hope this is sufficient to make sort of connection with buzzwords like needles in a haystack thing that you've heard in the news, et cetera. So it should give you a sense that really what it all boils down to is design of selections using information on a collision, and those are the fundamental core concepts of analysis, and everything else is then sort of details. And in order to understand data access, it really is just that. Processing to provide something, designing of a selection, measurement of yields, and accounting for efficiencies. Now let me talk a little bit about the basic data flow that we have today. 10 petabyte per second of raw info. I talked about trigger and zero suppression, gets you out gigabyte per second. That gets prompt reconstructed within a few days. I think the target today is 4, if I remember correctly. And then both the raw data and the output of raw prompt reco gets written to tape. And this short delay of a few days is there for 2 reasons. One, to have an immediate access to the quality of the data we're taking. So if something breaks, you immediately, within days, you have detailed knowledge of what verification that the reconstruction actually works with the instrument that we have. And the second is to, or in the early days of the LHC, it was very important for surprises, discoveries, and that sort of thing. In addition, there is 2 to 3 times as much simulation as there is raw data, and that also gets put to tape. And so a reasonable starting point to think about is that all subsequent processing and analysis starts with the decision of what data stays on disk and for how long, because the bulk of the primary data is all on tape. And the raw data will stay on tape forever. Occasionally, we delete certain entire reprocessing campaigns because newer, more recent data is available, and the older prompt reco gets deleted. And so we actually recycle tape. What stays on disk is then distributed into 150 petabyte global disk-based data federation, and there's about 200,000 core processing capacity across 50 to 100 clusters worldwide. And a lot of what I'll be talking about is, what do we do here? But before I get there, I want to say a little bit more on the nature of the data at the LHC, because it's useful to have some fundamental picture in your head of what the data looks like in order to understand why we do what we do. And I think the most useful picture in your head is to think of the data at the LHC as a 2D problem. You have events where the events is simply nothing more than beam in crossings. So every beam crossing that you collect is an event. And then you have objects that characterize the event. And so this is electrons, muons, mincing transverse momentum, et cetera, et cetera, et cetera. All of the 80 million channels digitized, put into meaningful physics objects that then get analyzed to characterize the events and make a selection. And so the choice of an analysis is literally a selection in this 2D plane. And I'll talk about this multiple times in this talk in order to justify how we do what we do. Let me already now at the beginning give you a little bit of a contrast of processing use cases in the context of this 2D plane, because it will show you the enormous dynamic range of what we do in terms of just processing. I've picked 2 extreme examples. The primary processing touches every single object in every event. It therefore is complete to good approximation on the entire 2D plane. Everything in the 2D plane gets accessed. It takes about 2 seconds or so on a recent physical core per event, and the LHC is expected to slow this down by a roughly a factor 24. In contrast to this, science analysis, meaning the stuff that leads to physics publications, touches data very sparsely. Typically 10% or less of the data per event is accessed. And it does down selects as a first step. Every analysis that I've ever seen selects, and I'll go into this more detail later, makes the down select a filter at the very beginning to bring the data volume down by orders of magnitude, because otherwise it wouldn't be manageable. So we are effectively making a copy up front that depends on 10% or less of the data to make the decision of which events are relevant for the publication that we're working on. Today, this is done at order 10 hertz, meaning 10 events per second. Contrast this with the 2 seconds per event. And for the high normal series C, we're shooting for a 10 kilohertz. In other words, 10,000 events per second. Compare this with about 50 seconds per event of the processing. So there is a many orders of magnitude difference in how, in the kind of processing that is done. And so what that means, the take-home message up front, and that's also how I structure the rest of this talk, is that the high normal LHC has really 2 data problems, not 1. And those 2 data problems have very little to do with each other because they're completely different in their requirements. And there is, to be completely fair, there are some special types of processing that are somewhere in the middle on a log scale, but the extremes drive the bulk of what gets done, especially at the high normal series C. Primary processing works at order 1 exabytes at order 100 seconds per event per core. On the previous slide, I said at 50, that's order of magnitude of 100. All data in the event is accessed. That is the primary processing. Science analysis works on order terabyte to petabyte. That's what I mean by, and I'll get more into this later, that's what I mean by pre-selection. But even before the filtering is applied, you already pre-select the exabyte into something smaller. And this is sort of more or less after you've taken the exabyte and made it a terabyte, and then you work with this terabyte regularly, is sort of the idea. Order 10 kilohertz is the event rate per core, and a small fraction of the data per event is accessed. And so I will now first talk about the first problem and then switch gear and talk about the next problem and second problem, because these 2 problems have so little to do with each other in their requirements. So let's talk first about the primary processing problem. We're currently discussing a multi-year program of work towards a large data challenge that would establish our capability in this realm, and the proposal for what this would look like is what you get if you click on this pointer, and I'll send Alex Sim my slides later so that they can be made available to people to sort this, to follow this link and look at more details. In a nutshell, the raw data processing at the high normal series C, each of Atlas and CMS want to do their annual processing campaign of previous year's data and simulations during roughly the first 100 days of the new year. In other words, we have a standard operating scheme that the accelerator turns on sometimes February, March, turns off sometime in October, November, and then we finalize calibrations and so forth as the actual software that is being used. And the final software and calibrations are then used sometime January, February, March in order to do a final reprocessing of that year's data. And that's the data that ideally is going into publications. And so in the high normal series C, we're talking about an exabyte in 100 days. And these are all order one digit significant figures, basically. So that would give you 10 petabyte of data per day for 100 days, or a terabit per second in terms of processing continuously. All data resides on tape across the tier 1 centers worldwide. In CMS, there are 7 of them, and roughly 40% of it is at Fermilab for CMS and at Brookhaven for Atlas. In other words, the US will host roughly 40% of this exabyte that gets analyzed in 100 days is early in the year for last year's data. This would mean the US portion of the processing is 400 gigabit per second. And even if we restrict just the raw and divide by 2 for the 2 experiments, so you divide by 4 total, you still get 100 gigabit per second for each experiment nonstop for 100 days in the US alone. This is a very large-scale processing challenge, and it brings with it lots of technical challenges. The technical challenges revolve around tape recall, managing limited disk buffers, managing a terabit per second network, managing disk buffers at HPC centers or whatever centers is used to do the processing, bring outputs back the same way, including storage to the archive, and do a co-scheduling of all of the above, because it is not reasonable, in fact, it's not financially sensible to assume that you have an exabyte tape buffer, disk buffer in front of the tape archive and bring all the data onto disk first before you start. That's just crazy. And so we assume that there will be a tight coupling of some sort between tape recalls and compute processing, and that in the middle, the networks will have to be transferring in bursts in order to fill buffers fast, so that the scheduling of preprocessing is reasonably steady state, and the tape recall is also reasonably steady state, and the network is used bursty. Aside on the transatlantic networking, I'll have a couple of these, given that ESNet has a special interest in that. In the early LHC days, each Tier 1 center was responsible for processing of data in archives. In essence, before we started the processing, before the LHC data taking started, we had a model that the Tier 2s have custodial responsibility, that the data they archive, and responsibility for doing the processing of that data. The assumption was that the networks aren't good enough to move data around the world as needed. In the intervening 10 years, Atlas and CMS have gotten used to transfer data globally to where there's processing capacity. In other words, that model is completely broken now. People simply transfer the data that it needs to be processed, often make multiple copies in order to maximize the flexibility of then and sending executables where the data is. And not just Tier 1s are used, but also Tier 2s. We've used the cloud on occasion. We use HPCs at some small scale today. So any processing capacity that there is, if you look at the scales here that I had on my previous slide, it is conceivable that the early LHC data is more like the early LHC, the early high luminosity LHC, simply because of scale and the networking it would imply, especially across the Atlantic. Now let me switch gear to the high luminosity LHC analysis data challenge. So the other challenge, and let me give you a little bit of sociological information of why this is not just technically different and why the technical differences make sense. The analysis challenge is sociologically a very different thing. And that is because each of Atlas and CMS has more than 1,000 scientists from a few hundred institutions in more than 50, well, it's actually, I should have written here more than 40 countries, apologies, that want to exercise their academic freedom to analyze this data to their heart's content. If you make the union of Atlas and CMS, then you get more than 50 countries, because there are some countries like Canada where CMS doesn't work. The objective in this is that innovation and science success depends on academic freedom. Another way of putting this is that competition drives innovation. So we collectively, as organizations that work towards a common goal, produce primary data set. So the entire first part, the first data challenge, is done collectively by the experiment as a whole. But then we let everybody and their brother and sister compete against each other for best ideas and best results. And then once we have a period of competition, we have a period of convergence where you have internal peer review such that publishable results can be agreed on by all, or by all who care, say. And so you, in essence, have in the data analysis infrastructure, we need to support the middle piece, and that's what it means to support a lot of freedom and a lot of flexibility, such that competition can drive innovation and you don't have too structured and too much management decisions that impede innovation. It's bottoms up rather than top down, basically. And in that context, it is worthwhile to look at event sizes a little bit more carefully. I've talked on the previous slides about the first two formats and ignored two other formats. And those two formats are really the formats that drive the innovation and the analysis. There is some amount of innovation happening around the objects and around the next version of the software that will be used to do the primary processing that happens at the AOD level, and very, very, very little at the raw level. CMS produces different size data formats for different purposes. And there is a hierarchy that each one can be produced from the previous. So nano is derived from mini, mini is derived from IOD, and AOD is derived from raw. And if you want a simple way of thinking about this, raw is the most flexible. Raw and AOD are the most flexible. They're also the slowest. Nano AOD is the easiest to use, and it's the fastest, but it restricts you. Some things cannot be done with nano because it only has, given that you're talking about 1 kilobyte or 2 kilobyte per event as data format, it is literally a highest level of objects, allowing no change anymore, or very little change, only change that is required by more than 50% of the analysis. So the kind of changes that everybody has to do is still possible, but any kind of reconstruction level changes cannot be done, or fundamental changes in what the object is defined as cannot be done on nano. For that, you have to redo it. And nano AD today can be actually analyzed at 10 kilohertz events per core. And it's a brand new format that was created only recently. So I'm going to now, so this is in essence what you should keep in mind when we're talking about analysis. Now I'm going to take a detour about simulations, because there's another whole dimension to this of diversity, and that needs to be understood in order to understand placement of data and movement of data and decision-making of placement on data. And that is that the science program is exceedingly diverse. Nature allows anything to happen in a quantum mechanical process that proton-proton collisions at this energy can possibly do. There's no steering. Whatever can happen will happen. And it's our job then to differentiate what are we looking for out of the totality of the mass of things that have happened. And so all imaginable physics that could be produced in the instrument and could be searched for, but may not be produced in the instrument, needs to be simulated. So the simulation, therefore, is massively diverse. There are thousands, literally thousands of small samples of limited physics interest. And then in addition to all of these things that you want to search for, or the rare things that you want to measure that you know that ought to exist, that drives this part of the data, there is a few dominant physics processes that are copious background processes for many searches. And those are actually finite and enumerable, whereas this set is just enormous. And so there's a much smaller number of very large samples that I want to say 50% of all analyses need to actually access in order to do their science. And so the access probability has enormous dynamic range, and I'll show that later. And that is fundamental to the physics program. It's not an accident. So the dynamic range of distinct physics samples in size ranges over orders of magnitudes. And in addition, given that we have a processing annually, there is an annual repetition for simulations that produce more or less the same physics, but with the latest version of the software. And so we have actually campaigns that happen annual that will repeat the simulations on previous years, just with new software, new definitions of objects, etc., etc., etc. And so you can think of a life cycle of a data sample that shifts over time because the same physics happens to appear with a new version of the software, and people will gradually move over time. And to give you a sense of scale, I'm showing you two plots on this slide and the next. And I want you to focus on one particular campaign. I told you that we have these simulation campaigns, and I'm going to pick on one campaign which has the mnemonic Run to Summer 16 DR80. I picked on this particular campaign because this was the main physics campaign for the simulation for the 2016 data taking. And it was just something that I had easily available to put in these slides from a review that we've done in 2017. And what you see here is the sample size per event on a log scale on the bottom, and the fraction of the sample count on the y-axis. The totality in this campaign was 14,000 samples. So there's 14,000 distinct physics samples that are the totality of the simulation in this campaign. And if you look at this pink or whatever the color is, violet, you can see that at roughly 10 to the 5, so at 100,000 events, samples smaller than 100,000 events make up 70% of all samples. So 70% of these 14,000 samples are small, 100,000 events per sample. Now, if you look at it in the opposite direction of sorts and plot the fraction of event count total versus sample size, you find that that 80% of the total of the events are in samples with greater than 10 million events. In other words, this part of the plot, the top of the plot. So if you again follow this violet curve, at this point it meets, and sort of I read off maybe 25 or so % here. So let's call it 80% is above. It's really 75 probably, but let's not rough numbers. Roughly 80% of the total of all events produced in this campaign were in samples with greater than 10 million events. If you look at these two statements that we just have inferred by just looking at what was produced for the main production of the 2016 in physics simulation, you can immediately see the enormous dynamic range of what we're dealing with in terms of simulation samples. Now, the obvious thing to expect from this is that we should expect that most samples are rarely accessed because they're probably going to be, the vast majority of samples are going to be of limited interest. And so that's exactly what you see. And what in this plot is shown, again, number of files in a log scale on the y-axis, it's the number of times that a sample got accessed in a month on the USD tier 2. So what you're looking at is you pick a US tier 2, 1 of 7. You look at every file that was accessed in the month of whatever the states are, and then you count how many times was this file accessed, and then you put that accordingly into one of these bins here. That means, and if you then look at the distribution, it's hyper-exponential. The most likely time that something is accessed, if it's accessed at all, is once in that month. And then it goes down to the most heavily accessed file is accessed 150 times. And so this kind of distribution, of course, lends itself poorly to an LRU type access mechanism. And I will come back to this in more detail later. So it shows you that the fundamental nature of the science leads to a very peculiar access pattern, which is not going to be changed by technology choices because it is driven by the way we do physics, and that's driven by the physics that we do. It's not the choice we have. It is fundamental. Let me now switch gear again a little bit and talk about infrastructure. From here on out, I'm going to talk about infrastructure plan for the LHC. The kind of thinking that we have up to here, I've motivated why we do what we do in building the infrastructure the way that we want to build it for everything that comes from now and the rest of the talk. And the first thing to introduce is what we call the data lakes model. This is the current straw proposal, if you wish, for how the LHC wants to organize its data and the access of data for the high level LHC. And I'm going to walk you through, there's a lot of details here that has not been decided. And so at this point, we have a high level concept that now needs to be filled with technical content over the years to come. But some things are already reasonably clear. We're talking about more than one lake globally. For example, the US might have one lake per atlas and one lake per for CMS, and therefore the US may be, the entire US infrastructure in play may be divided up into two lakes, and those lakes will get data via managed processes from other lakes. There might be another lake in Europe, and there might be a third lake in Asia, for example. Or maybe the rest of the world makes one lake. We don't know yet. There's a central managed replication between lakes. In other words, while today we have means to actually stream data across the Atlantic, in the future we may not. At least currently the model allows for a definition that there's no streaming across the Atlantic. Intra-lake data access is then mixed via multiple mechanisms, and what will be used for what mechanism is yet to be determined as we understand better what is best. There's going to be some top-down placement. For example, as part of workflows, as I defined in the very beginning, the first data challenge is basically a top-down placement that would work really well in the context of a top-down placement as part of these giant workflows. The second one is a bottoms-up placement for cache misses, and that is more likely to be the model adopted for analysis because it makes more sense there. And then you might have streaming for remote file opens. And the notion here is that small sites may not want to be supporting disk space at all because managing file systems is a pain in the you know what. And so it may be advantageous for building regional centers that share disk space and some amount of streaming from remote. And I'll talk more about these two both. And at this point, we're at the position where we're starting to explore the features that this model has with a mix of R&D pilots and production pilots to gain understanding of what works well, to do analytics on our use cases, to basically refine the model to arrive at something that is cost effective for the high-level LHC. An aside on networking, data lakes model implies, and I think said this already, that there is no streaming across the transatlantic. That also means that it lends itself to managed transatlantic links. We could use things like Sensor to control the high-level LHC data transfer across the Atlantic. Similarly, within the US, CMS will likely want to flag flows according to broad use categories. For example, the top-down placement that is part of large production workflows may want to get different kind of priority than the bottoms-up placement or the streaming. And so we may want to tag traffic with 3 tags according to these lines of use, and then dynamically change the priority of these on different links over time. So you can see that these kinds of things lend themselves naturally to collaborations with ESNet. Then next, I want to go into one particular production scale caching pilot, because caching is at least presently perceived as a central part of this data lakes concept. And I want to explore that a little bit more. And to set the stage, Caltech and UCSD are tier 2 centers for CMS. Each has about 10,000 cores, give or take. And they currently operate a joint petabyte disk cache. And so why is this joint? The network latency between Caltech and San Diego is 3 milliseconds. That's one of the closest centers, and therefore one of the most obvious places in the world to do something together. we have created a distributed caching infrastructure that has disk space in Pasadena, disk space in San Diego, and that disk space is coherently managed as one entity via a what we call a redirector. And then all jobs that run in San Diego or Caltech that want to access any mini AOD or nano AOD, these are the two analysis formats that I mentioned earlier, will access this joint cache. And therefore, you have streaming across from Pasadena to San Diego for sort of kind of half of the total load, if you on average. We then have started, and this is literally the very beginning, we've analyzed at some point a period of time in 2019 to get a sense of what's the working set. In other words, we ask ourselves, given that we have this cache, and what is actually going on when people use it? And so we define a working set as the sum of sizes of all files accessed in a time period. And here you have an entry for the working set per day, per week, and per month. And we sliced it up out of curiosity between simulations and data. And you can sort of see that for this time period, the working set ranges from a few tens of terabytes daily. That's the top plot. This is 5 and this is 35 terabytes. And to a few hundred terabytes monthly, and that's what you see down here. To give you a specific number, the working set for October 2019 was 451 terabytes. That is the sum of all files that were accessed, the sum of the sizes of all files that were accessed in 1 month in the Southern California cache by any job that accessed those caches. Next, we can do file reuse measurements. And what we define here as the reuse is in the numerator, we just count up all accesses to any file and then sum the file sizes. And the reason why we define this as the numerator is because if you work on a model where you have to bring the entire file in every time a file wants to be accessed, then this is the relevant size. In other words, not having a cache and bringing instead, copying the file always as it is needed gives you the numerator. And having a cache and only summing up the unique set of files that were accessed in the time period is the denominator. So the ratio between the two is the multiplier that is the savings in network bandwidth, if you, or in a certain way of thinking about it. And you can see here a time series. These are the dailies. So the average daily is somewhere between 1.5 and 2. So even for the daily reuse, we save somewhere between 50% and a factor of 2 of the network traffic by having caches rather than just accessing everything from remote. And in addition, of course, there's savings in CPU time, because if you were to say, I'm going to stream everything from Fermilab, say, then a job would have to wait until the data arrives before it can start processing. And that would waste CPU time because it already occupies a batch slot. And now, next observation is partial file reads. I've mentioned this, and I will show you why this is happening in the next slide. But let's first look at it, just what we observe. When we look at the ratio of actual reads, meaning the actual read, the amount of data served by the cache to the executables, divided by the naive reads, where the naive reads is just this numerator here, the actual file size that was accessed, that ratio is somewhere peaking around 10%. And you can sort of see the distribution. This is the daily average of all accesses. And you can sort of see that the daily average is flopping around. Here we have the daily average plotted as a time series, and you see that there is occasional days, as shown here, where jobs run that access 60% on average of all the simulation. So there are some outliers, but on average, you have sort of in the neighborhood of 10%. So the data formats of CMS are designed, the data formats for CMS that are meant to be used for analysis are designed to support these partial file reads. And I will explain next how that is done and also why that is done, because the physics that we do drives these choices. They're not random. And so let me show you this again by going back to our 2D structure of data. I told you that a fundamental activity of any science at the LHC is that you have to select on some objects a subset of the events that are relevant for you for the science that you want to do, because the nature gives you all science that you can do, and any given publication needs to focus on a tiny subset of what's relevant for that publication. And so a typical application running through the data therefore picks a few objects, makes a selection of those few objects to define whether the event in question is relevant. And then if the event in question is relevant, accesses a few more objects. So the red here indicates the objects that are being accessed by an executable. And the 2D plane, each box here is an object in an event. And as you can see, there is a good motivation based on the science that we're doing that this access pattern is always very sparse. There's very little science, if any, that is justifiable that would actually lead to non-sparse accesses. Therefore, the data format needs to support this kind of behavior. And let me talk a little bit briefly on how we do this. And it relates also to data integrity. I'm going to discuss it in the context of data integrity, but fundamentally, we do this because it allows for reuse. It allows for the partial file reads. So we define something that's called a basket, and the basket is per event a certain width of number of objects. In our 2D space, it's basically a square or a rectangle. A rectangle is really the right thing, not a square. A rectangle, and different objects fall into different baskets and different types of rectangles. So I've enumerated these baskets here by going from the left to the right, and the left to the right is number of events. And then our data format compresses each basket, and the compression has two side effects. One is it saves us disk space, and two, it enforces data integrity. If we, for whatever reason, in our file-based data transfers have a bit flip because of broken infrastructure somewhere, that bit flip will generally, in fact, close to almost certainly, lead to an unreadable file because you can't uncompress the basket that has the bit flip. At the same time, you can only support partial file reads to the extent that the objects that you've packed, the objects that you need here, say these two bands, are in the same basket. If you design the data format badly at the time that the files are written, you basically make partial file reads impossible. And so there's a lot of thought that goes into the data format for different types of processing. Now I finally arrived at where I've given you now all the information that is necessary to understand the three core research topics for the second part for the analysis challenge, basically. And I'm going to pick on my three favorite R&D topics in the analysis data use case, and I'm going to then discuss them in context. And the first one is better cache miss algorithms than least recently accessed, LR, no, what is, whatever U stands for. Then how large can a region be for a regional cache? And finally, can we exploit partial file reads to save disk space? In my mind, those three are the potential drivers of cost reductions of the total amount of disk space that we need in order to get the science done, based on all of the arguments that I've given in the last 36 slides. So let's talk about beta cache miss algorithms first. There is really crucial information on a sample in its metadata, because in the sample metadata, we record what's the physics content of the sample. Therefore, if you know the metadata, you know whether this sample is among the very obviously accessed by many people, because it's one of the core pieces of physics that everybody needs to access because it's background to many analyses, or whether this is some obscure something or the other that nobody other than the one person who will write a paper on this will ever access. And so therefore, the sample metadata is actually incredibly useful to make caching decisions. Similarly, a processing campaign is potentially useful for a caching decision, because I told you that annually we reproduce the same physics with a new release of the software. And so it is useful to learn where is the collection of users of the data as they switch from one campaign to the next. Have they already switched and I therefore can delete all of the old campaign data? Or do I have to keep the old campaign around because the vast majority of people haven't switched yet? And both of these can in principle be learned, and it ought to be useful to predict the future use better than just recording what has not been accessed in the last little bit of time. And so there's a group at INFN that is developing an AI algorithm. Basically, they've picked a deep learning architecture and are trying to implement this and see whether indeed you can play back past use traces and prove that if we had used this AI algorithms, we would have made better caching decisions. And this will then lead to deployment if they come up with something that's worthwhile. And this could then lead to disk space savings. Next topic is how large can a regional cache be? And to see this, it is worthwhile to look on the map. And to remember that sociology is a very powerful tool to make infrastructure decisions. And to be blunt, Italy has, for example, a vested interest in organizing themselves into one region and then run one cache for the entire country. Similarly, Spain has this, similarly the UK has this, and if you then look at distances, you quickly realize, gee, this actually would work really nicely if our IO stack could tolerate 500 miles as the round trip time equivalent of 500 miles as in going from south to north of Italy and so forth. So a reasonable goal to arrive at an infrastructure that has operational costs that are well defined and easy to support would be to get an IO stack that is sufficiently latency tolerant to lose less than, say, 10% in CPU time for access distances of 500 to 1,000 miles, because that would allow you to make regional caches that span entire countries in Europe. And given that a lot of our resources are in Europe, that is a very reasonable and rational way of thinking about this. And that brings us to, given that the only production cache worldwide that exists today in CMS is the one in Southern California, and that is our playground to figure this out and watch production happening. ASNet was kind enough to give us another cache, and well, it is placed 470 miles by chance away into Sunnyvale, which is therefore a very relevant distance for the distance between entire countries in Europe. And so in early May this year, we added that cache to the Southern California infrastructure. And we don't have data yet sufficient to show you that this actually works and how well it works in the wild, but at least I wanted to show you something that is actually being used. So these two are plots that Diego made yesterday, if I remember, either yesterday or the day before, I think the day before maybe. And it shows the daily number of accesses on the y-axis and date on the x-axis for jobs accessing the ESNet cache. And you see it peaks around 5,000 accesses, and you see the turnout in the beginning. And at this point in time, 2 terabyte is about here. So at this point in time, we have about roughly, we read about 2 terabytes a day from that ESNet cache. That means that jobs executables that run in Caltech or San Diego will open files from disks in the ESNet a cache that is deployed at the Sunnyvale POP. And the objective of this exercise is to gain experience of operating a regional cache. It's the first regional cache in the world for CMS. And we will be, among other things, we will be comparing CPU time over wall time. Basically, take a given executable that runs in San Diego or Caltech, measure its CPU time over wall time when it accesses data locally, or when it accesses data across the network from ESNet in Sunnyvale, and see whether there are systematic differences and how widespread they are. And I'm interested not just in the averages, but more even in the distribution. How many executables are there that actually have a significant drop? That sort of thing. Then my last topic I want to talk about is exploiting partial file reads. I've argued that researchers analyze that partial file reads are here to stay and that they are fundamental to the science. In addition, what I haven't told you yet is that a typical publication analyzes in the order of maybe 24 data sets with the same executable. So a known quote-unquote executable, meaning the physicist who does the analysis knows what he's running, and he's going to run the same code on 24 data sets. And in principle, if there is then an obvious question, if we knew how to detect which executables belong to which publication, in other words, which executables are the same as they run over these 24 data sets, and if we then could learn the access pattern in real time, we might be able to predict how the remaining terabytes are accessed from the first gigabyte. If such a thing was possible, at least within the same data set, then we could maybe make decisions on partial file caching that would further reduce the total amount of disk space necessary. So you can I look at this in 2 ways. Either we could learn it via some kind of artificial intelligence, or we could give users, the physicists that actually know for sure what they're doing, the tools that they can define declaratively what they're going to do. And therefore, we could use that declarative input from the researcher in order to do something intelligent. At this point in time, it's, in my mind, completely unclear how to best exploit this. This is probably the most esoteric, the most unknown of all of the things that I've described. And nevertheless, we're putting the hooks in place to actually exploit this potentially. And that gives me an insight on what we call analysis facilities. The LHC community is considering a paradigm shift from analyzing its data sequentially along the events axis to something that we call, or I don't know, maybe the computer science community calls it that way. I have no idea where the name comes from. Declarative programming. In essence, given that the name of the game in our science is to define a selection and then loop over events that selection defines a filter on events. We loop over events and loop over large volumes of data, filter, define objects on the fly, add those objects into the object content per event, and write something out. That's what we do today. If instead the researcher were to define the selection in a declarative way, and then we could leave the quote-unquote compiler and infrastructure, the loop, then you could make intelligent decision behind the researcher's back, so to speak, and it wouldn't be, and you could actually make infrastructure level decisions on how to use data in order to save money by saving disk space. And because this sort of declarative program paradigm would open up a whole more predictive and speculative analytics way in defining the 2D plane of objects that are really relevant. And the initial pilot projects that we have walking in that direction show orders of magnitude speedups. So at the processing end, we already see the massive benefits of doing this. What we haven't done yet is we haven't analyzed at all yet what could there be in terms of disk savings and infrastructure cost savings by doing this. And that research program hasn't even started. However, what has started is we have a design hook to exploit it if we can figure out what it is that we implement to exploit it. And so that runs under the buzzword Service X. Service X allows transformations to be applied on the data as it enters the cache of the analysis facility. So that is the right place in the architecture to implement any kind of things that you would learn from this sort of inquiry. So if there was indeed something to be gained by filtering events, filtering objects in the event, do some sort of intelligent processing of the 2D plane such that not everything has to be put on disk. Even reformatting to change bucket structure could be done here to support faster use of access. There could be user-specified code running inside Service X which gets you to the declarative programming. What exactly would get done in Service X right now is unknown, but we're in the process of producing the software artifacts, infrastructure software artifacts that would allow us to implement this kind of thing. And the next step in my mind is to do the R&D to understand what's the use case in detail. Does it even make sense? What's the killer app basically? What's the killer app for Service X that makes the biggest savings impact on our infrastructure? And I think that gets me to the summary and conclusions and to the Q&A. The high-performance LHC expects an exabyte per year data by 2028. It's a times 30 increase over today. This has led over the last couple of years to a careful re-examination of what we do with our data and why. And to me, arriving at where we are today with having a clear picture of why do we do what we do and what are the possible architectural features that we can exploit to do better was really essential to now ask the question, which of those features gives us how much cost saving in reality? And that's sort of where we're at. We identified promising R&D to save on disk space needs via a mix of network caching and tape archiving and a combination of top-down, bottoms-up, and direct access to data. That's it for me. Questions?
Okay, you can unmute yourself to ask questions. And it's a little past afternoon, but let's give some questions if you have.
So this is Eli. I have one. Thanks, Frank. This is great. I have I have a question about, so, you know, you're talking about sort of different scientific investigations require different subsets of the data, right? You're talking about sparse access and things like that. Do you anticipate different types of scientific analyses having different data access patterns? And so it might be useful to have, say, 3 caching methodologies, depending on how different analysis codes might use the data?
I think that the answer to the first question is unambiguously yes. We know today that the different and physics analyses lead to different access patterns. It's not obvious that they lead to different caching and decisions. What they do is in the context of service X, the level of filtering that's possible for different analyses is very different. And it's even for the same analysis on different data sets, it is very different. And the easiest to understand is the example of analysis driven by leptons, electrons, and muons. The total production probability at the LHC of an electron or a muon is tiny compared to with the total production period. So electrons and muons are incredibly good probes for filtering out the total. Now, in the simulation, you then have to ascertain how much fake electron or muons do you have that in order to understand the analysis and the result. And so the filter efficiency on a sample that doesn't have true electrons or muons versus a sample that does have true electrons or muons is orders of magnitude different. And so if I say that one publication requires 12 or 24 data samples on input, even for one executable, its access pattern across these 12 samples will be orders of magnitude different. And in the sense that, where was I? In the sense that how often you pick the 5 objects out of all objects is in one case maybe 50%, and in the next case 10 to the minus 3. Does that make sense?
Yeah, it does. It almost sounds like you're talking about different access patterns for simulation versus experiment data, for example.
And even within the experiment data, yes, that is certainly true. But even in the experiment data, so what we do, when I talked about going from the 10 petabyte per second to the 1 gigabyte per second, part of that is already a bucketing. We bucket in about a dozen buckets,
right,
the data that comes out of the detector. And we make in real time a decision on whether a data stream that has at least 1 lepton of high PT, a data stream that has at least 2 leptons of high PT, a data stream that deliberately was not selected based on leptons, but based on missing transverse momentum. Another data set that was selected based on B tags. So we have all of these physically motivated and ultimately motivated by understanding of what's the relative production probability of different kinds of objects in a collision. That motivates already the first 12, say, different buckets as the data comes out of the instrument. Am I making sense?
Yeah, okay.
So there are decisions made, real physics, real science decisions that are made already in hardware, in the trigger, in the instrument, and similar kinds of, and they actually then determine an access patterns later, right? If you run if you're searching for leptons in the sample that wasn't selected for leptons out of the instrument, you're not going to find many leptons.
Indeed, right. Yes, exactly.
And it's those kinds of decisions. But the physicist knows this, right? So there is, when I do an analysis for a publication, I know exactly which is which. So I have an enormous amount of information on the expected access patterns that right now I don't communicate to anybody or anything. If we had more of that kind of thing, that expected behavior patterns, including learning, so there's an enormous amount of thing that could potentially be exploited, but we're not right now. And it's not obvious how much it can be. We don't understand the scales completely to really say this is going to guarantee to be exploitable, or, well, maybe not. Does that make sense?
It does. It does. Okay. Thank you.
Any other questions?
I've got a question. I realize this is a presentation mostly about the big concerns you have around data motion, data formats, data access patterns. I was wondering whether you could address whether maintaining performance of your analysis applications themselves on new processing architectures like new CPUs, GPUs, accelerators is comparatively important to the data issues. Does the data motion, data format, and access pattern problem kind of outstrip the performance concerns that you might have, or are they equally important?
Yeah, let me answer this question with this slide in mind. This part here, collectively produced primary data sets, accounts for, what did we look at yesterday? Give me a moment to remember. I believe we concluded yesterday that 92% of all CPU power required, currently assumed to be required for the high-performance LHC per year, is bound into this process. So this here is 90% of the CPU power total. This here is 10% of the CPU power total. I've talked about data exclusively. This here is where all the costs are accumulated in data, because this is completely top-down managed, and buffers, assuming that we control buffers intelligently, that is minimal cost in disk. So in a way, here is where all the disk costs go, and here is where all the CPU costs go. And your question is fundamentally, crucially important here, because if we were able to offload more of our CPU needs into the accelerators, then our footprint for processing here shrinks dramatically, and therefore our cost shrinks dramatically, at least in principle. And so what you've asked is, to me, there's really two important questions in order to reduce costs for the high-performance LHC. How much can we make use of accelerators in the fundamental primary processing reconstruction algorithm? And how much can we save disk space in the fundamental secondary and later data analysis? If we make progress on those two fronts, then the high-performance LHC project as a whole becomes affordable. Does that answer your question?
Yeah, thanks a lot.
And as you can see, these two questions completely separate. They have nothing to do with each other.
Frank, can I follow up just briefly on that?
Yep.
So you're answering, I want to know whether your answer to Roland's question is from a CMS perspective or from a CMS and Atlas perspective, right? Does what you just said hold true for Atlas also?
I think there is a little bit of a yes, but not quite so extreme.
Okay.
meaning traditionally, so if you let me think of where that is. I don't have a slide that speaks to this. Traditionally, Atlas simulation of the detector has been much more CPU costly than CMS. I don't know the exact numbers, but it is very significant. And as a result, the relative proportion today that Atlas spends in GEONT in the full simulation is larger than CMS. But the cost evolution for both is the same, in that the detector simulation scales very softly from now to the high normal series suit, whereas the reconstruction CPU cost scales dramatically. So when I put here, I forget where this was. When somewhere I had a factor 24. Yeah, this factor 24 is common to both Atlas and CMS. Maybe in Atlas this factor is 30 or 20, I don't know, but it's very, very similar. So the reconstruction becomes much more costly for fundamental reasons that are common to both experiments. Atlas starts with a larger cost of the simulation, and therefore it takes them a little longer for the reconstruction to completely overwhelm the simulation cost. And so the exact details of the number work out differently, and I don't know them on the top of my head. I happen to have looked at the CMS numbers yesterday. Maybe instead of 92% in this first part, maybe it's 80% or something. But I don't think that it is fundamentally different. Does that answer your question?
Yes, thank you. Well, for entities that have to support both experiments, right? It's useful to know sort of how closely these things are, or how similar they are. So thank you.
And I think when it comes to, in principle, from the physics and the science and the knowledge of what we have of our simulations with instruction, et cetera, et cetera, et cetera. Let me put it differently. I have seen and looked at and studied the parameters that go into the Atlas cost predictions and the parameters that go into the CMS cost predictions. They're, for all practical purposes, close to identical. I mean, they're not identical, but they're very, very similar. So in principle, infrastructure should work for both. In practice, the experiments make choices on how they want to do things, not how they must do things. And that's sort of where then the differences show up. Does that make sense?
Yeah. Yes, thank you.
Any other questions?
Hi, this is Harvey. I have a question. When talking about service X, are they at all conscious of the difference between this kind of subsetting and random access, trying to do that to a spinning disk?
Yeah, I mean, the notion is that one possible and talked about effect of service X could mean that you end up using the desire. The ideal future scenario would be that service X becomes such a killer app that the stuff that you start storing is small enough that you can actually store it in random access media and no longer have spinning disks for the output that comes out of service X.
Well, it's important anyway because there's literally a factor of 1,000 in terms of the number of
and so there is a hope that the utilization of non-spinning disks, meaning random access media, will become an essential part of the infrastructure because we're exploiting this kind of structure. To what extent we'll be successful remains to be seen. Because if you think about this, service X may be in the wrong location architecturally. It may have to be moved down here, right? Because if you're thinking of it actually being if you had to store the stuff that comes in on spinning disks, and then the stuff that gets accessed in the executable on SSDs, then there would have to be a service X-like piece down here between the CPUs and the spinning disks and the cache, so that the cache suddenly becomes hierarchical.
Yeah.
And that is unclear right now. I think that's a level of optimization that hasn't been thought through. We're good?
Yep.
Any other questions? Okay, thanks everyone.
Thank you, and sorry that I went so far over.
This is very helpful, Frank. Thank you.
You're welcome. It was very helpful for me to force myself to make this because it's been helpful to get my head